Hello students, welcome to EPG Pathshala. I am Dr. Manjula Sharma from University of Delhi. Today we are going to talk on the module Important Instrumental Features of SEM and TEM, that is Scanning Electron Microscopy and Transmission Electron Microscopy under the paper Measurements and Instrumentation. After completing this module, the students will be able to understand the important instrumental features of SEM and TEM, basic electron optics, electron optical elements and attachments, electron source, the thermionic emitters, and the field emission gun. A scanning electron microscope or SEM is a type of electron microscope that produces images of a sample by scanning the surface with a focused beam of electrons. The electrons interact with atoms in the sample, producing various signals that contain information about the sample's surface topography and composition. The electron beam is scanned in a raster scan pattern, and the beam's position is combined with the detected signal to produce an image. SEM can achieve resolution better than 1 nanometer. Specimens can be observed in high vacuum in conventional SEM or in low vacuum or wet conditions in variable pressure or environmental SEM, and at a wide range of cryogenic or elevated temperatures with specialized instruments. The most common SEM mode is detection of secondary electrons emitted by atoms excited by the electron beam. The number of secondary electrons that can be detected depends, among other things, on specimen topography. By scanning the sample and collecting the secondary electrons that are emitted using a special detector, an image displaying the topography of the surface is created. The image shows a working scanning electron microscope setup. The various parts have been indicated by the numbers. Part number 1 is the electron emitting gun. 2 is the electromagnetic lenses in order to direct and focus the electron beam path inside the column. 3. Pump system for vacuum. 4 is the opening to insert the sample into the high vacuum observation chamber in conventional SEM mode. 5. Operational panel with focus, alignment and magnification tools and a joystick for positioning of the sample. 6 is the screen for menu and image display. 7 is the cryo unit to prepare, break, coat and sublimate frozen material before insertion in the observation chamber in cryo SEM mode. 8 is the electronics stored in cupboards under the desk. The image here shows a working transmission electron microscope setup present in a lab. Now students, let us see the basic electron optics. Electrons and ions are charged particles. They can be accelerated in an electric field. The trajectory of an accelerated charged particle can be changed or deflected by applying an electrical or magnetic field. The accelerated particles also behave like waves, that is, the de Broglie waves. A schematic of the transmission electron microscope is shown in figure 1. It shows the electron gun, the accelerators, set of first condenser lens, after that the second condenser lens. After this arrangement, the specimen is placed. Below the specimen are the objective lens, the intermediate lens, and finally the projector lens. The electron beam travels through all these lenses and the specimen and reach to the fluorescent screen. And below the fluorescent screen is the photographic film, and below it is the CCD camera. The basic components of the transmission electron microscope are the electron source, that is the electron gun, with associated accelerating facility for engineering the electrons, a set of lenses, that is the condenser, objective, intermediate, and projector, a fluorescent screen on which the final image is observed, and photographic facilities for recording the images. In addition, there are apertures introduced in the vicinity of the condenser, objective, and intermediate lenses and stigmator. The specimen stage normally takes in a sample of 2.3 or 3 mm diameter, either mounted or supported by copper, carbon, or beryllium grids. The specimen stage has facilities for tilting about one or two axes and rotation. It is also possible to heat, cool, or strain the sample while under observation, that is, heating, cooling, and straining stages. The functions of the lenses are: first, of the condenser lens, to control beam intensity, density, and convergence. For the objective lens, the first stage of magnification facilitates the formation of bright field and dark field images. And the intermediate lenses, they further magnify, and imaging and diffraction mode can be made possible by using them. And finally, the projector lens, these are used for the final magnification of the image. The basic components are the electron gun, lenses, double deflection coil, detectors, and stigmator, along with the scan generator and cathode ray tube for observing the image. A light microscope and scanning electron microscope are similar, as both are used in the reflection mode. The main difference in these microscopes is that in light microscope, whole of imaging, the entire specimen is performed at once, while in SEM, the electron beam is scanned back and forth over the specimen, and thus imaging is performed at only one point at a time. The interactions of the electrons with the surface are registered, and from this data, an image can be constructed. The relationship between the area scanned on the specimen and that on the monitor is shown in figure 3, and the concept of magnification is illustrated in figure 4. A block diagram of the scanning electron microscope is shown in figure 5 with the various parts labeled. As with TEM, it is possible to tilt the sample in the SEM along one or two axes. The various components of the SEM are: on the top there is electron gun, then there is beam monitor aperture, then condenser lens 1, after it is the gun valve, then the objective aperture, after that is the condenser lens 2, then the deflection coils, then the objective lens, and at the bottom the specimen is placed. The various components in the SEM can be summarized as follows. First, a source, that is the electron gun, of the electron beam, which is accelerated down the column. Next is a series of lenses, that is the condenser and objective, which act to control the diameter of the beam as well as to focus the beam on the specimen. Last is the series of apertures, that is the micron scale holes in a metal strip or film through which the beam passes and which affect the properties of the beam. Controls of the specimen position, that is the XYZ, the height and orientation, that is the tilt and rotation, are also provided. An area of the beam or the specimen interaction that generates a variety of signals that can be detected and processed to produce an image or spectra. All these components are maintained at high vacuum levels, the value of the upper part of the column being greater than the specimen chamber. Students, the electron optical elements and attachments are electron source, lenses, deflection coils, stigmators, electron detectors, and photon or X-ray detectors. Now, first of all, consider the electron source. Generation of electrons that can be accelerated by high tension to obtain the illuminating electron beam. The sources are of two types: thermionic gun, triode or self-biasing gun, tungsten, lab 6, cerium boride 6, and field emission gun, which consists of single crystal tungsten. The photographs of the two types of guns are shown in figure 6. A part shows the thermionic emitter, that is the tungsten filament, and B is the field emitter. Now, let us consider the thermionic emitter. A schematic of the thermionic emitter is shown in figure 7. Electrons are emitted from a heated tungsten filament at a temperature of 2700 Kelvin and then accelerated towards an anode, which is a flat plate with an aperture and is earthed. A large negative potential is applied between the filament and the anode. The vanilled cylinder is biased slightly negative from 0 to 500 volt with respect to the filament. The electric field of the gun causes the focusing of the electrons at the crossover region. This region has a size of around 50 micrometers. The current density Jc of the electrons from the cathode is given by Richardson's law, that is Jc is equal to AT square into exponential minus EW by kT ampere per centimeter square, where A is the Richardson constant, T is the emission temperature, EW is the work function, and K is the Boltzmann's constant. For the tungsten filament, the values of A and EW are 60 ampere per centimeter square Kelvin square and 4.5 electron volt respectively. For a typical temperature of 2700 Kelvin, the value of Jc is 1.73 ampere per centimeter square. The maximum value for beam brightness, that is beta, is given by the expression beta is equal to Jc EV by NKT, where E is the electronic charge and V is the accelerating voltage. Using the value of 1.73 ampere per centimeter square for Jc and with the accelerating voltage of 100 kilovolt, the beam brightness is found to be 2.37 into 10 raised to 5 ampere per centimeter square. The anode plate assembly acts as an electrostatic lens. A divergent beam of electrons emerges from the anode hole. Tungsten filament is the most commonly used electron source. It is robust, cheap, and does not require relatively high vacuum. The relationship between beam brightness and filament heating current for a tungsten filament gun is shown in figure 8. Brightness goes up with increase in filament current up to a certain limit, beyond which no further gain is observed. Increasing the current beyond the saturation limit results in excessive heating of the filament, leading to filament failure, an effect that is clearly seen in figure 9. Students, there are three configurations for the lanthanum boride cathode depending on the heating method. The Breuer's type employs a tungsten coil enveloped around a sharp end of a stretched around 2 cm lab 6 rod. Heat radiation and electron bombing from the tungsten coil heat up the tip end, and the transference of heat through the structural support assists to reduce reactivity of lab 6. In the Vogel configuration, a short lab 6 rod is heated directly by transient current, perpendicular to the length of the rod, using firm electrical connectors that also offer the provision for the rod. Pyrolytic graphite is used in between the conductors and the rod to evade the difficulties of chemical reactivity of lab 6 and the conductors. In the Ferry's configuration, a short lab 6 rod is maintained by a ribbon or belt through which an electrical current is passed for heating. The rod is heated by conduction from the ribbon. The ribbon material is chosen to be chemically interactive or chemically inactive with the lab 6, such as graphite or tantalum. The details of this configurations are shown in figure 10, ampere per centimeter square, Kelvin square respectively. Therefore, the brightness of the lab 6 is an order of magnitude higher than that of tungsten filament. Energy spread in thermionic filaments is due to filament imperfections, high tension instability, variations in surface temperature, and First effect, that is mutual interaction. Typical source spot sizes are 30 micron for tungsten and 5 micron for lab 6. Now students, let us consider the field emission gun. Field emission refers to the emission of electrons that are stripped from the parent atoms by a high electric field, typically 10 raised to 9 volt per meter. The field emitter is a single oriented crystal of tungsten, electrolytically etched to a fine tip, with the tip diameter of 100 to 1000 angstroms. A field emission tip can be cooled or thermally assisted to help overcome the work function. The temperatures are lower than those required for thermionic emission. The process requires very good vacuum. A simple tungsten tip can be very sensitive to surface contamination. More than any other cathode design, the field emission tip is extremely sensitive to the size, shape, and surface condition. The work function of the metal is responsible for the emission process. This work function can be affected by the adsorbed gases. This is the reason for the very high vacuum requirement. Sustaining high electrical field gradients is similarly important to emission. So, a tip that is well damaged might not produce electrons at all. As with the tungsten filament gun, the voltage alteration or bias among the voltage first anode and the accelerating voltage on the cathode regulates the emission current. The second anode is at ground potential and the voltage difference from here to the cathode determines the acceleration given to the electrons. The shape of the anodes is carefully selected to minimize the aberrations. And field emission guns are schematically shown in figure 11. The basic difference is the presence of an extra anode which applies the high electrical field on the filament tip and the considerably higher level of vacuum in the field emission gun. The important points to note are the considerably higher level of brightness, lower energy spread, and therefore minimized chromatic aberration effects, and the longer life of the FEG source. Stringent vacuum requirements and the considerably higher cost are the limiting factors. The tungsten filament requires a considerably higher probe size for carrying the same probe current compared to the FEG. Lab 6 and FEG are preferred for carrying out high resolution electron microscopy and when using very fine probes in X-ray analysis. The tungsten filament is good enough for most of the routine applications. The magnification level in a SEM can be varied over a range of about 5 orders of magnitude from 25 cross or less than it to 25 lakh x or more. The image magnification in the SEM is not dependent on the power of the objective lens, which is unlike optical and transmission electron microscopes. The function of condenser and objective lenses in SEMs is to bring the focus of the beam to a spot and not to image the whole specimen. Provided the electron gun can generate a beam with sufficiently small diameter, an SEM could in principle work entirely without condenser or objective lenses, although it might not be very versatile or achieve very high resolution. In an SEM, magnification results from the ratio of the dimensions of the raster on the specimen and the raster on the display device. Assuming that the display screen has a fixed size, higher magnification results from reducing the size of the raster on the specimen and vice versa. Magnification is therefore controlled by the current supplied to the XY scanning coils and not by objective lens power. So students, let us summarize what we have learned in this module. We have basically learned about the important instrumental features of SEM and TEM. We have learned about the basic electron optics. Then the electron optical elements and the attachments have also been described. We also learned about the electron sources. We also learned the thermionic emitter, and towards the end we learned about the field emission gun. Thank you.